Okay. Good afternoon, everyone. I'm Ankit, and I'll be talking about how to reduce the depth of a size S circuit to depth 3, and I will be bounding the size, the blow up in the size. So in the last talk by Ramprasad, what we saw was that if you start with a size S circuit for a degree D polynomial, then f can be represented in this form. So there might be some factor here, some maybe 15D or 9D or whatever the constant factor was. I'm ignoring it just for the sake of convenience. But everything I present does not depend upon this. It only requires an upper bound, where the degree of all Qij's is at most root D. Again, there might be some constants here. So in this talk, what we will see is that actually you can further reduce. So what is this? This is a depth 4 circuit. Why? Because each Qij is a polynomial, so it requires a depth 2 circuit to be computed, and then you are multiplying these polynomials, and finally you are taking the sum. So it's a depth 4 circuit. And in this talk, what we will see is that you can further write this expression in the form where so you can write this expression in this form where the degree of each Li is at most 1. So these are linear polynomials. And moreover, this reduction will only work over the rational numbers. So this is only true over rational numbers. Oh, okay, sorry. Okay. Okay. Okay, so we will use exactly this as a starting point, and slowly we will apply a set of reductions to arrive at this form. Okay, so the first question that we'll be yes, okay. So the first question that we'll be asking is that let's ask ourselves whether you can write this expression into a seemingly simpler form, which is that all the polynomials you are multiplying in this term are the same. So in particular, can you further squash this down or simplify this expression into something which looks like this form? So can you write say s to the order root d? Can you write this in this form? So we can ask ourselves this question, that when can you further simplify this expression in this form? So note that this might not always be possible to do. Why? Because for example, if you are working over a field, let's say, where the characteristic is 2, and if we ask ourselves, can we express xy as sum of powers of two polynomials, then the answer is no, right? Because whenever you will because the character is 2, and when you will expand it, the coefficient of xy will be divisible by 2, so it will be 0. So xy can never be expressed in this form. So certainly such sort of a reduction, this statement, we cannot expect it to be true over all fields, but it's a legitimate question nonetheless. When can we do this? And if we can do this, how much is the blow up in the size? Do we require a lot of such summands, or such an upper bound will suffice? Okay. So actually this question has been studied separately, and to answer this, and we will look at this in a separate thread. So I will leave this thread for now, and I will start a different thread. Okay, maybe on this board. So here one asks the question of what is the complexity of computing a product using only powers and sums. So I will represent a power. So in this question, so in this model of computation, this model of computation is what is called a powering circuit. And such a circuit has two types of gates. An addition gate, which is the same as what we saw in the morning, which we have been seeing till now, and the other kind of gate is a powering gate. This is not an AND gate. This is a powering gate. And the question is that we want to simulate a product, right? We want to compute a product of n things, but the only operations we are allowed to use are additions and powers. So let me define these gates. The sum gates are the same which are used in normal arithmetic circuits, which we saw in the morning. They just compute the sum of the inputs. And a power gate, there is a predetermined degree associated with such a power, or a power associated. So it takes an input f and it just powers it and outputs it. And the question is, what is the size of a circuit which is built on these gates to compute a product? Okay, so to get a feel of this question, let's start with, again, as before, let's start with the smallest depth, which is depth 3. Okay, so let's start with depth 3 powering circuits. Okay, so such a circuit, the output gate is a sum gate. Then there is a layer of power gates, and finally there is one more layer of sum gates. And then there are inputs or constants. So note that this layer will compute a linear polynomial, arbitrary linear polynomial. Then it goes into a sorry, this is a unary gate. This is the wrong picture. This can only have n1. What this gate will do is it will raise it to some prefixed arbitrary power, and then there is a sum gate which takes sums of many such powers of linear polynomials. And if the size of the circuit was s, then note that this in degree is at most s, so there are at most s summands, right? So this boils down to the question, how many, so one particular question you can ask is, how many such summands do you need to express a product into this form, into sum of powers of linear polynomials? Okay, so using the actually inclusion exclusion in some sort of Riser's formula which we saw in the morning, one can show, or this was shown by Fisher, and a variant of it was also appeared in Amir's thesis, that 2 to the n suffices. That you need at most 2 to the n summands to express this product into this fashion. Okay, so let's see a proof of this. So in particular, the formal statement that we will see is that. So let me just. Okay, let me write on this board. Let me write it. Sorry. Or maybe. Okay. So the formal statement that that he showed was that n factorial. Let me just use a different pen. So what it says is that you are just so every term, so you are summing over all subsets of the n of a set containing n elements, and you are just in every term you are just picking the xi's which are appearing in the subset. And the claim is that if you will see the coefficient of, if you will see the polynomial computed by this, then it will exactly be equal to this. Note that there is a multiplication by n factorial, so you require the field to have large characteristic, because there is, in some sense, there is a division by n factorial. So again, we are, I mean, this is true only over fields which have large, so in particular rational numbers. Okay, so let's see a proof of this. The proof is like, yeah, we have seen. So let's see again. It will be more clear. So note that the proof is one line actually. Note that this monomial can only be contributed from a term from the term for which s equals n. Why? Because if this term does not contain all the variables, it can never produce this monomial, right? And in particular, this term will be just and then there is the multiplication by -1 to the n minus mod s, which is 1, because mod s is n. And what is the coefficient of this monomial here? It's just the multinomial coefficient in which you are taking 1. So it is just, which is like n factorial by, which is n factorial, which is exactly this. So I just need to tell you that if a monomial, every other monomial has coefficient 0. So in particular, what we want to show is that if a monomial does not, note that all monomial produced here have degree exactly n. So that means any other monomial will be missing at least one variable. So without loss of generality, let's assume that the monomial whose coefficient you are looking does not contain xn. So let's say m is x1 to the e1 up to xn minus 1 to the en minus 1. Okay? So I will show that the coefficient of this monomial here is 0. So to do that, let's split this sum into two parts. Sets that contain n and sets which do not contain n. So you can split this into two parts. You can write this as S. So these are the subsets which don't contain n. Okay. Plus summation of all sets that necessarily contain n. So I can again write this subset as, I can take a subset from the first n minus 1 elements, and then just take the union. So it will be again, but note that now I am taking a union with xn, so there will be this, right? And here I will have okay, clear enough? So let's just take, so let me take this common. So this goes away. So I'm just removing this. I'm taking this summation common, and there will be a minus sign which will be left here, right? I'm sorry, I'm hand waving a little bit because this is something which we have already seen in the morning. And now you can ask the question, what is the coefficient of m in this term, in this polynomial? And I claim it is 0. Why? Because coefficient of this monomial from this term is exactly the same as for this term, because xn will not contribute in it, because this does not depend on xn. So you might as well assume that it is not there, but then you get the same thing. That's it. That's the proof. Okay, so we have seen this statement, and now I will be using, we can use this identity to just reduce this expression into a simpler form. We can reduce the top product gate and make it into a power gate, which is certainly a simpler form. Okay, so let's use this identity. So what this identity says is that consider one term, which is, let's say, x1. So any term, let's say root d. So if you substitute this there, it says that this is going up to at most 2 root d, right? So it is some linear combination where this is some of the QIs. I mean, yeah, QIs. Some subset of QIs. I mean, it is some alpha I QI, right? Up to root d. Some linear combination might be this is Boolean or not Boolean, doesn't matter. It is some linear combination of QIs. Okay, so let me call it just right? Oh. Moreover, note that because we started with the assumption that all these QIs have degree at most root d, in particular, every linear combination also will have degree at most root d. So QI tilde has degree at most root d. Okay, so we have simplified this expression. The thing the question that we asked, we have answered this. So if your field has large enough characteristic, then you can certainly simplify this expression to this form. But you are getting a blow up of 2 to. You are getting this blow up of 2 to the root d, which is something which we can tolerate. S to the order root d times this, you can always absorb this term in this blow up into this expression. So this is okay, right? Okay, so note that we have eliminated the top product gates and we converted into powering into. We are just taking powers, converted into power gates. But if you view any QI, okay, let me just write down. Yeah. So here, if you view any QI, now we want to apply the same identity again. I want to further simplify this. I want to remove the product gates again. I want to replace every product gate with a power gate. So I want to further simplify this. So if you view any QI, this can be written as just into some. This is just some alpha I times xi1 up to xi root d, right? Because it's a degree root d polynomial. So any such polynomial can be written into this expression. So let's apply this identity again. So applying this identity again on this monomial, we will get this further can be written as this n to the root d comes because there are at most n to the root d distinct monomials of degree root d times some alpha I. And then there is, okay, let me just move this. J. There is I, right? So you are taking the ith expression and you are writing it in this form. So in particular, this can be absorbed, this can be written in the form some k equals 1 to n to the root d times some right? So this QI can be further simplified in this form. So in particular, we started with this form. We first reduced it to this form. And further, we can write this expression in this form. Yeah, okay. Right? Till now, everything is clear. Are there any questions till now? Okay. All right. So now note that we are in this form. We are in this form, and we want to go to this form. We want to go to a depth 3 circuit. And we are already in this stage. Now, if I were to trivially expand this polynomial out, if I were to expand this term out, this is the power of a linear form. So if I will expand this out, I will certainly arrive at this form, right? I want a product of linear polynomials. So if I will just take this term, expand it out, I will arrive in this form. So what is the problem? The problem is that there are n to the order root d summands here. And then you are taking, you are summing them and you are taking the root dth power. So if you will expand it, you will get n to the order root d to the root d such terms, which is a blow up we cannot afford. So this is like n to the d. So d is like poly, n is like poly, so this is like n to the n, which is something which we cannot tolerate. So we need to do something clever. So to do that, we will go again back to powering circuits and we will look at the next step. Okay? And then I will tell you that a previous work by someone else already had encountered exactly the same problem, and he was able to circumvent it, and we will use the same way to circumvent our problem. Okay. So here we use something known for depth 3 powering circuits. So the next depth is depth 4 powering. So let's see the polynomial that a depth 4 powering circuit computes. So a depth 4 powering circuit has a sum gate as the output gate. Then there is a layer of power gates. And then there is a layer of addition gates. This is a unary gate. It only has one input. And again, there is a last layer is a layer of power gates. And then there are variables. Okay. So what does the bottom layer compute? Any such gate computes just a power of a variable. So it is some xi to the e, right? Then there is a layer of addition gates, and it takes sum of many such powers of variables. So in particular, you can always write the output of such a gate as a sum of univariate polynomials, right? It's just a sum of powers of variables. Then there is a layer of power gates, so it powers this. So it's to the sum power e. I mean, okay, maybe e prime something. Right? So this is good to n. And then finally there is the output gate is a sum gate. So the output looks like sum of powers of sum of univariates. This is the polynomial outputted by such a circuit. And you can ask, can you prove a lower bound for this model? So the point is that, well, at the time the first lower bound came for this model, there was already a lower bound known for a slightly different model, which was sum of products of univariates. Or at least that's the way I see this proof, that there was a lower bound known for this model, and you want to prove a lower bound for this model. Now again, you can always convert this model into this model by just trivially expanding. If you were to trivially expand this term out, you will get a product of sum of products of univariate polynomials. But again, the point is that if you trivially expand it out, you'll have a huge blow up. And then you cannot use the lower bound here. So to circumvent this, so Saxena gives something called a duality trick, a version of which also was proven by Spilka and Wigderson. So what does this identity say? It says that you can actually expand this out, you can convert this term into this form very efficiently with a very small blow up. So what is the statement? It says that suppose you start with x1 plus up to. Okay, let me start with then this is just sum of Okay. So you can always write this into this form. But here you need the field to be containing at least nd plus 1 elements, because we would be using interpolation. So now let me tell you the proof, and I will write down the formal statement and we will prove this. Okay, there's plenty of time. Okay, maybe on. Okay. Okay, I will give. Okay, so let's see a proof of this. So the formal statement I will be proving is that x1 plus 2xm whole to the d equals, or actually there exist so for every distinct md plus 1 elements in the field, there exist beta ij's in the field such that times okay. So this is a product of univariates. This is alpha I. This is only depending upon there are only md plus 1 alpha i's. Okay? And the proof will be just by interpolation. So let's see the proof. I will rub this, okay? Okay, let me rub this. Okay, so to prove this, let's define a polynomial p of z to be x1 plus z up to xn plus z. Okay, there is a m. Okay. Okay. Oops, sorry. This is m. Okay, so let's start with this polynomial, and I want you to visualize this polynomial as a polynomial in only the z variable. So imagine that yi's, the xi's are constants. So so imagine this as a univariate polynomial in z, and note that this polynomial and is z to the d plus z to the d minus 1. And this proof, oh, by the way, this proof that we will be seeing is due to Spilka. So, so this polynomial is z to the d. Is z to the m plus z to the m minus 1 times x1 up to xm plus z to the m minus 2 and other lower degree terms. So these are the lower degree terms, right? But note that I want you to convince yourself that coefficient of z to the m minus 1 is just sum of xi's. So what is p of z minus z to the m? It is just z to the m minus 1 times x1 to xm plus lower degree terms. Okay. Now, what do we need? What do we need here? We need a dth power of this. We need a dth power of this. So let's just take a dth power of this polynomial. So, is it okay? Maybe it's a little bit too late to ask that. So let's take the dth power of this polynomial. So it will be p of z minus zm whole to the d equals plus lower order terms. So it is z to the m minus 1 t minus 1 and so on. Right, because this is the leading coefficient, so this is the leading term, so it's z to the m minus 1. If you will take the dth power, the coefficient of z, the leading coefficient here will only depend upon the coefficient of leading coefficient in here, right? So it is exactly this what we wanted. So now note that this is the term we require, and this is occurring as a coefficient of this polynomial. It is one of the coefficients of this polynomial. So now we can just use interpolation to extract out this coefficient. So we know that so what we know is that any coefficient of a univariate polynomial can always be expressed as a linear combination of the evaluations of the polynomial at least d plus 1 distinct points where d is the degree of the polynomial. So what is the degree of this polynomial? The degree of this polynomial is m times d. So if we take any distinct alpha I, so alpha 1 up to alpha md plus 1, any md plus 1 distinct points in the field, then we can always express this coefficient as some linear combination, so let's say gamma I, some linear combination of the evaluations of this at alpha I, right? This is what we saw in Amir's talk. One of the things we saw in Amir's talk. Sorry. So, right, so till now everything is clear. This is using just what we saw. Okay. So, so let's see what this P alpha I is. P alpha I is a, I'm sorry, it's not P alpha I. This is minus alpha I to the m, right? Right, everything is okay. This is the polynomial. So let's just expand this out. So if you expand this out, this will be summation of j equals 1 to the important part. The important part is only that this is a scalar. So this part will go up to degree d. So this is some degree t, so times some gamma j tilde. We don't care what this scalar is. Phi to the j, right? We are just expanding this out, and you can always write it in this. So let's simplify this expression a little bit. Let's take this out. So this exactly is what we require. This is some beta ij. Right. So what is P alpha I? P alpha I is this is PZ. So P alpha I is exactly this. That's the proof. That's it. This is exactly what we wanted, right? Okay. So we have this identity, and here what this tells us that actually you don't need to trivially expand. You can do something much clever. So if we come here, this is exactly the problem that we were also facing when we were here. We could not trivially expand this out because that would be too costly for us. So let's try to just see what happens if we use this identity here. So let's focus on one term, and we will plug this. We will see what if we apply this identity to this term. Okay, so let's see that. Okay, so the term we have is some L1 to the root d So if we replace every xi by li to the root d, what we will get is, by this identity, it is, so m here is n to the order root d, so it will be n to the order root d. D is root d, so it will be root d. Okay. And then this is summation to root d, because d is root d. And then there is beta ij is L1 to the I. Oh, sorry. Thanks. Thank you. Right? So this is, so note that this is almost a depthy circuit, but this is not a depthy circuit because this term, if you look at this term, this is not a linear polynomial. So this is not a depthy circuit. In depthy circuit, you have products of linear polynomials, but this is not exactly a linear polynomial. But note that you can further ask, so let me just make things more clear. Let me go back again and ask the question, what happens if you have powers here? So let's say you had a root dth power here. Okay, so because this is exactly the problem we are encountering. So also, let me, for the sake of clarity, because we could choose any arbitrary alpha i's, let's pick alpha I, choose our alpha I to be minus I, so it's minus outside, to the root d. So it is I is an integer, you are taking the root dth power and then you are negating it. Okay, so let's take alpha I to be I to the minus I to the root d. So what we will have, because this reduction works for any distinct alpha i's, as long as they are distinct, it's okay. So if we plug this here into this expression, or here in this expression, what will we have? We will have, this is just minus I to the root d. Okay, but now what do we know? We know that any x to the root d minus any I to the root d, this can be factored over the complex numbers as maybe it's 0. Right? You can by fundamental theory of algebra, you can always factor this into this form, where omega is the root dth principal root of unity. So we get this. Now note that it is also true here, so this is also true for any L. So any L can be written this form. You can replace x by L, still the identity holds. So this term, which the problem we had was this was not linear, you can factor this and now you have a linear polynomial, right? So you can so now this can be further written down as is the same summation beta ij, and here you have product of, right, so you have okay, 2n to the order root d, then you have just I'm just writing this product into a more compact form so that I can replace each of them in this way. So this is this will be L. So you can again expand this out using this identity. So this will be right? And this is a linear. This is a depth 3 circuit. But note that there is a omega. There's a root of unity involved. But still, what we have shown is that if you start with a size S circuit for degree D polynomials, then you can squash it down to depth 4 circuits, where the bottom Fanon or these Qij's have degree at most root D, and we only have a blow up of S to the order root D, right? And now what we have shown is you can further squash it down into a depth 3 circuit of similar size, but this is over complex numbers, because there is a root of unity involved. And in a minute we will see how to eliminate that root of unity, but till now, but at least what we have seen is that if you started with complex numbers, then this depth reduction holds. That you can always depth reduce to a depth 3 circuit. So one of the corollaries, so actually in a minute we will see that you can actually get, if you started with rational numbers, you can further simplify this circuit to have a rational circuit. The coefficient will only involve rational numbers. So in particular, a corollary of this is that, so we know that determinant has poly-n size circuits, right? So in particular, what this implies is that determinant also has depth 3 circuits of size. So this is the takeaway message, that determinant has depth 3 circuits of size n to the order root n over rational numbers. So in the morning we saw Rice's formula, which for the permanent, and it was a depth 3 circuit. If you recall, it was sum of products of linear polynomials, but the size was of the order 2 to the n, where n is the n by n matrix. And here, for the determinant, you are getting a much smaller depth 3 circuit, which is size n to the order root n, so you save a lot. Also, the difference is, one important difference between the two is that Rice's formula, which we saw in the morning, so every term which you were summing, every summand had degree exactly n, at most n, I mean exactly n. So there the individual terms were not blowing up in degree. It was very it was a homogeneous circuit. But here, if you observe, the intermediate degree is going up to n to the order root d. So this is, and determinant has degree n. And the intermediate terms have degree, are producing, so intermediate computation is producing polynomials which have degree going up to n to the order n to the order root d. So which is really big. This is heavily non-homogeneous circuit. And later on, when people will present lower bound results, we will see that this is something which you require. You cannot have a circuit like Rice's formula for the determinant with this much size. It's provably not possible. Okay, so now let me tell you how to eliminate this root of unity. If you are happy with complex numbers, then there's no need to eliminate it. But if you really care about rational numbers, then let's see. So we have 5 more minutes. Let me show you how to eliminate the root of unity. Okay. So I'm not going to formally prove it, but I'll give you a basic idea. And the basic idea is, again, just interpolation. Okay. So say so suppose I give you some f1 plus little omega g1 times up to fk plus omega, or some power of omega, say, I mean something I1, ik, gk. So suppose I give you a product of polynomials involving roots of unity. So let's say it's of this form. Certainly every such term is of this form, right? So suppose I give you such term. And moreover, fi's and gi's, you know that fi's and gi's are rational polynomials. So they do not involve, they only involve rational numbers. Now I ask you that can you, from this small circuit, computing a polynomial, let's say h, can you extract out a small circuit which does not, so and let me also say that h, the polynomial you want to compute, you know that it only has rational coefficients. Remember that the polynomial that we started with, right here, f, we started with a circuit which was over rational numbers. So it did not involve any complex coefficients. So we know that the polynomial which we are trying to compute also does not involve any complex coefficients. So it is over rational. But suppose here we are given, and I ask you, can you extract out a smaller circuit which only involves rational numbers for h? So the way to
Polynomial we're trying to compute is the sum of such polynomials, right? So
okay, this is not bad.
how do you know that each one of them is rational?
I'm just starting with this expression. This is the expression I want to simplify. So I only wrote down an expression which is analogous to this. It is not a general question. I only want to simplify this.
You have a sum of these, not just one.
Ultimately, if I can simplify one of them, I can simplify all of them individually.
Yeah, no, is it clear that each term on its own is rational when you expand?
No, it's. I mean, yes, it's not clear. But what is clear is that these LIs that we are getting, these LIs, those are rationals. I ultimately I want to only extract out the rational part of this, and at the end I want to sum. But by the way, I will. So you are right. Your question is a very legitimate question. I will not be extracting out the rational coefficients. I will just be extracting out a small circuit for this. Okay, so the point. Okay, let me just write down. So note that this term can be written as. So let's say the total. You have a bound on the total degree of omega i's. Okay, so let's say these individual degrees are at most say d, and that is the only thing I will require. So let's say they are at most d. Now I want you to visualize this term, this polynomial, where omega is a variable. Forget about that it's a root of unity. Think of this as some variable omega. It's a variable. Okay. So if this is a variable, you can always write this polynomial by grouping the coefficients according to the monomial of this variable. So you can write this down as h0 omega 0 plus h1 omega 1 up to so on h k d, because each I is at most d and there are only k such products. So the total degree will be at most kd times omega to the kd. This is certainly you can do. Now we will use interpolation, and by interpolation we know that each hi is just some linear combination. Note that the rest of the things are rational. So the linear combinations we are getting are rational. This is something which also follows from the original construction. So this is some j to the 1 to the kd plus 1, say beta j times let me call this term t times so right now I'm not summing it. Forget about the sum. I don't care about the sum. I'm only caring about one term. I will do it individually for them. So this is say t. Okay, so this is not t. Right, where alpha j is the same, some distinct elements over the rational field. Right, so this is something we know, which we saw in the morning. Right, this is something which we can always do. So this is h. Right, till now everything is clear. I mean, the last part might be confusing, but everything is okay. If you have questions, please ask. So you can always express every such hi or every coefficient of an omega I in this expression, right? Now, because this is a root of unity, the actual polynomial, so note that this is a depth circuit, because what you have done is that every alpha, every h of alpha j, you have replaced this root of unity by some alpha j. So now the new thing you are getting is a depth circuit. It's just a product of linear polynomials. This was linear, let's say this was linear, this was linear, this was linear. So the ultimate thing you are getting is a product of linear polynomials, but now everything is rational. I'm talking about h of alpha j. So was this is okay? So note that this is only over, you have eliminated the root of unity. The only thing is that because this is a root of unity, this satisfies, I mean here it was, well, let's say it was a ds root of unity, so it satisfies omega d to omega to the d equals 1. So there will be the actual thing which is, so this term will be simplified to, okay, let me just take this to be iota. Okay, for now, let me just say this was iota. For the sake of simplicity, I think it will be good for everyone. So let's say this was I, and this was I. Okay, so what will be this? The rational part, so this term always can be written as h tilde 0 plus h tilde I. It can always be written in this form. Whenever you have an, I mean an odd term, so you send it to h0 and the even term goes here. This can always be written, right? And that's it. You are only taking the rational part here, and this part you will be ignoring. So this part, just take this part. This is the rational part. That is the proof. Okay, maybe this was hand waving. I don't know. Should I go over this part again? So here what you will be doing is that you have omega to the k. So the only difference you will be having is that instead of I squared to the 1, you will have a relation like omega root d. Because this is a root d at principal root, you will have this relation. And now you will have to apply this relation. So you can write this expression into h0 plus h1 omega plus this is tilde, h2 tilde omega square up to h root d. And now you compare the rational parts. This will only involve, this is rational and this is multiplied by omega, this is omega square, there will be no cancellations, and this is the part that you want, the rational part. That's it, it's the same proof, exactly this, nothing else. The important thing to note is that the blow up here is again very small. The blow up was of the order of the degree of the term. The degree of the term here is n to the order d, so here you will have another blow up of n to the order d. But it is okay, something which we can tolerate. This will be just this thing times n to the order root d times. This is okay for us. That's the proof. Okay. So that was the depth reduction to depth 3. That's it.